No questions? All right, well, let's continue on then with what we were talking about last time. So last time we talked about what an orthogonal set is, what an orthonormal set is, and then extended that to, or perhaps we narrowed that down to, is a better word, orthogonal and orthonormal bases. And we talked right at the end of class about why we care about such things. So if we have a basis, just to mention what we talked about right at the end of class last time, if we have a basis, orthogonal or not, the idea behind something being a basis is that anything in my vector space I can write as a linear combination of the basis vectors. We've talked about that before. If it's orthogonal, then I can figure out what the coefficients are that we need for our linear combination by basically projections, right? So if I take this W and dot both sides with the V sub I, if it's an orthogonal basis, then everything over on the right-hand side gets killed except for the I vector, because they're all orthogonal, so their dot product is 0, their inner product is 0. And then I can solve for the C sub I by dividing out by the V sub I dotted with itself. And again, we know that's not 0 because we have a basis, means the 0 vector is not in there, which means the inner product with itself is not 0, so we can divide. So these coefficients that we get in our linear combination that gives us W really are just the coefficients of the projection of W onto each basis vector. This is a nice property. If it's orthonormal, we get even a better, we get even a better result, because if it's orthonormal, what is that inner product going to equal? 1, right? And so the coordinates, those coefficients, the coordinates with respect to the basis are literally just the dot products of the vector we're interested in with each of the vectors in the basis. Okay. All right. So let's see if we can use that idea. These are the same two bases that we talked about last time. So then, and that was in our first example and our second example. In this first example, we had an orthogonal basis, but not an orthonormal basis. In this one, this was orthonormal. Okay. So if we want to find the coordinates of this vector that we have, the 3, 5, 10, relative to that basis, we take the 3, 5, 10 and dot it with each of the basis vectors and do the inner product. In this case, when we get the inner product, we get what? 3 plus 10, so we get 13 on that one. We inner product with a -4, 2, 0, and get what? -12 times 10 gives us -2. It's an equal sign. And the last one, if I do 3, 5, 10, and the inner product with 0, 0, 5, we get 50. We agree? Okay. So then when we take the 3, 5, 10, that will be 13 over, I need to do the inner product of the first vector with itself. The inner product of the first vector with itself will be 1 plus 4, so we get 5. So we get 13 over 5 times 1, 2, 0. It should be a minus. And the other one, we get a 2 over. If I do the inner product of the second vector with itself, I'll get 16 plus 4 gives me 20 times the second vector. And finally, the last one, I have 50 over 25 times 0, 0, 5. We should be able to check that that actually works, assuming we did all of our arithmetic correctly. So then the coordinates, and remember our notation for coordinates looks like our Euclidean notation. There's 3 basis vectors, so we would have 3 coordinates. your components of that vector, so I'll just reduce it, I mean negative 1/10 and 2. And just to emphasize that I'm talking about the coordinates of this vector with respect to this basis, I'll put a little subscript of an S there. That's an S. Looks kind of like a 5, but that's an S down there. The coordinates with respect to the basis are the coefficients that you would need for each of the basis vectors to give you the linear combination. And again, the reason why we had to put the denominators in here is because this is not an orthonormal basis, it's just an orthogonal basis. So I have to divide out by the lengths, the squares of the lengths. That one okay? Again, the second one's a little bit easier because why? We already saw that this basis was orthonormal. When it's orthonormal, we just need to compute the dot products, and those are our coordinates. Okay, so we would compute 6, negative 18, 32, inner product with 1/3, 2/3, 2/3. But we're a little bit smarter. When I made this example, I would have not made a 32 because it would have canceled out 3. What do we get? 2, when we do the first product, negative 12 for the second product. So 2 minus 12 will give us negative 10, and then that's 64 over 3. Negative 10 is 30 over 3, so negative 34 over 3 for that one. Assuming I did it right. That's what calculators are for, right? The next one, we'll dot it with a negative 2/3, negative 1/3, 2/3. We get what? Negative 4 plus 6. So we get a positive 2 when I do the first two. We get a negative 4 plus a 6. So we get a positive 2. 2 is the same thing as 6 over 3. I'm going to get a 64 over 3 again. So I get 70 over 3 for that one. Like I said, it would have been nicer if I would have made something divisible by 3 in that last component.
The first product to be positive.
Say it again.
64 thirds minus 30 thirds.
Oh, yes, it should be a positive. Thank you. So I said it's what calculators are for, right? Now with negative 2/3, 2/3. Yeah, 1/3. What do we get? Negative 4 minus 12. So we get negative 16. 16 is the same thing as 48 over 3 minus 32. So I get negative 30. What did I just say? Negative 32. And then the other one was what? 36? Is that what I said?
48.
48. Thank you. 32 and 48 is 70? 80. 32 and 48 is 80. I think. Yeah, it's 80 over 3. It's skipping on me. Let's use the other one. Maybe I'll use the other one. All right. So then your coordinates of that vector with respect to the basis that we had was 34 over 3, 70 over 3, negative 80 over 3. Again, since it's orthonormal, we don't need to divide by anything, right? We just have to do the inner product. We're dividing by 1, so there's not a lot of work to do. It's okay?
In the previous, where do you get the denominators from?
The denominators, we're doing the inner product of this with itself, of each one. So we're doing this part right here. Yep. Yep. Other questions? So we talk about a process that allows us to convert any basis that we have into an orthonormal one. Okay? So that's where we're headed. To talk about why we might want to do such a thing, one of the things that we're going to talk about in the next section is needing to worry about having a projection of one vector onto a subspace when we start talking about least squares solutions. So let's talk a little bit about that so we have a lead into it. All right. So let's say we have vectors W1 and W2. This W1 and W2 in the picture are in this plane that I drew that is representing the subspace. Okay. So W1, W2, they're orthogonal to each other, and they generate this two-dimensional space the way I have it. I've got some other vector V3. This is sticking off of my subspace in some sense. And I want to talk about projecting V3 onto the subspace. Now, remember we talked about last time, we talked about projecting one vector onto another, right? If I had one vector and I wanted to project another vector onto it, we went down perpendicularly, right? Okay. We're doing the exact same thing here on this particular picture, right? I'm going from the tip of V3. I want to take the line that goes from the tip of V3 that would be perpendicular to this plane in this picture. That would give me the projection, okay? So this dotted vector here that I see that I've drawn between W1 and W2, that vector would be the projection and it would be orthogonal to this thing sticking up. Okay? All right. So the idea is, how do I get the coordinates of this V3 with respect to the W1 and the W2? Just like we did in the previous example, okay? So that's our goal here, all right? So how do we get to that goal? Like I said here, we dropped this perpendicular. We dropped this perpendicular straight down. I don't know why I'm not drawing anything. Drop this straight down. So this would be perpendicular this way, right? What I'm going to do is I'm going to write my V3 as a sum of two things. So again, I said that this vector right here would be the projection of V3 onto the subspace. So using that similar notation that we did for projection, except that what I have down here, I can get it to erase, is the subscript of a W, so that's representing that I'm doing a projection onto the subspace. Okay. This vector right over here then would be the difference between those things. It would be V3 minus the projection onto the subspace. Okay. So that's all I'm doing here. That's just what the picture is, right? Okay. The way we've constructed things, this V3 minus the projection has to be perpendicular or orthogonal to everything in the subspace. In particular, it would be orthogonal to both W1 and W2. And remember again, a way to check orthogonality is to do inner product, correct? Okay. So I would have a W1, its inner product with V3 minus the projection has to be 0, and the same thing has to happen with W2. All right, so again, I told you our goal was to try to figure out what these coefficients have to be, right? That was our goal, try to figure out what the coefficients have to be, okay? We just did that a little bit ago, but let's go ahead and talk about how we can get it in general here. Pardon me. Goodness. Okay. All right. So if we recognize that if I do the V3 again, let's talk about the V3 is your projection of V3 plus the V3 minus the projection. What happens when you take the inner product of W1 with both sides? What can I do with the W1 with respect to this plus sign here? With the dot product. What can I do with the dot product of W1 with respect to that that plus sign? Distribute, right? When I take that W1 and distribute it to the second piece, what am I going to get?
Zero.
It's going to be 0, right? Because this is what I set up here, right? This particular subtraction, this vector, is orthogonal to everything in W, right? So it's orthogonal to W1. So when I take my W1 and dot it this way, that part becomes 0. Now remember again, our projection of V3 onto W is some vector in W. I can write it as a linear combination, and the idea was that we were supposed to try to figure out what this A1 and this A2 are, right? Alpha 1 and alpha 2. So let me replace it that way. Oops, that's a W. And we already said that this inner product will be 0 when we distribute, right? So all this next line is I have W1 inner product with the projection. What can I do now with the W1? I can distribute again, right? But remember, what are we assuming about W1 and W2? They're orthogonal. So again, when I distribute to that second term, I'm going to get 0 again, right? So now we have, let's just go over here. Now we have W1 inner product with V3 is alpha 1 times W1 inner product with itself. And now I can divide again, right? So our alpha 1 will be W1 inner product with V3 over W1 inner product with itself, which looks familiar, doesn't it? Yep. So again, this is the coefficient of what you would get if I just project V3 onto W1. So what do you think alpha 2 is going to equal? That's what the also part's going to be. What do you think alpha 2 should equal?
W2 gotta get V3. W2 gotta get itself.
It's the exact same set of rationale, right? Just replace your W1 with W2. You'll get the exact same work. Literally the exact same thing. So, generally speaking, your projection of V3 onto W will be, pardon me, your projection of V3 onto W1 plus the projection of V3, oops, I should say W1, of V3 onto W2. Okay. Yes.
How did you get alpha 1?
How did I get alpha 1? I solved for it, right? I divided. Here was my alpha 1 here. I divided. Yep. Okay. Okay. All right. So we did this example because we could see it a little bit more easily. Not really an example, it's a verification. We could see it easily for two vectors. If I start adding more vectors, it's going to be the same type of formula. Okay. So we get to what we refer to as an orthogonalization process. So the idea here is that if I think about these three vectors being in R3, if I started with this vector and this vector being orthogonal to each other, we just created a third one, right? And if these were an R3, I just created an orthogonal basis because I have enough vectors now. Okay, so that's what's getting us to what we refer to as the Gram-Schmidt orthogonalization process. Now, I was teaching it, and he mispronounced Schmidt in class. So it became the Gram-Dung orthogonalization process. This was rather amusing, actually. All right, so anyway, this is the orthogonalization process. So you're going to start with a basis, okay? That's important. Some basis, doesn't matter what the basis is, as long as you have a basis to start with, okay? Just pick the first vector. We'll let W1 be the first vector. Okay? The first step in the process is to project W1, project V2 onto W1. So here's the idea. Here's my W1, okay? I've got some other vector, my V2, sitting up here, okay? I project down. This gives me the projection. Oops, I wrote my perpendicular sign backward. That gives me the projection, doesn't it? When you do the subtraction of V2 minus the projection, I now get a perpendicular vector, right? I get an orthogonal vector, don't I? Right? So now what I've done is I've replaced V1, V2 with W1 and call this one W2. They're going to generate the exact same subspace, but W1 and W2 are orthogonal to each other. Okay? Do it again for the next one. I now have W1 and W2. Project V3 onto the span of the W1 and the W2. We talked about how to do that, didn't we? It's the projection on a W1 plus the projection on a W2. Subtract. That gives us our third vector. And then you can just keep doing this over and over again until you run out of vectors. Okay? This is the orthogonalization process. By construction, when you're done, you get an orthogonal basis. Okay? Basically what you're doing is project the second vector onto the first, create an orthogonal vector. Take the third one, project it on those two, create an orthogonal vector. Okay? Take the next one, project it onto those three, create an orthogonal vector, and keep doing that over and over again until you run out of vectors. Okay? All right? Yes?
Step 4, what's the other type? SI.
Step 4. What other?
You say compute the projection of W.
This part here?
Yeah.
That's coming from this. I have W1 and W2. I need to compute the projection down. This is what we did all this work for. That was this part. It's coming from here. Yep, that's where it's coming from. Yep. All right. So let's do an example because that's a lot of letters, all right? Let's do an example. Example or 3 here. All right. Let's do an example. How would I check that this is a basis, by the way? What do you do to check that it's a basis, just to remind? Planets being linearly independent, which means we do what? Make a matrix and row reduce. Exactly, right? You would make a matrix and row reduce and see that you get a pivot. Basically, you get its row equivalent to the identity matrix, right? When you're done, the reduced row echelon form is the identity matrix. You should know how to do that. We've already talked about how to do that, all right? So we're going to assume this is a basis to start with. If it's not, we're going to run into problems, okay? We'll have an error in our process. All right, so here's how we construct our orthogonal basis. The first thing is your W1 will be just the first vector, okay? That first vector, W1, is just 1, 0, 1, okay? That's step 1, okay? The next thing we want to do, again, let me just label these as V1, V2, and V3 so we can refer to them. don't know why it does that. So let's do the projection of V2 onto W1. How do we do the projection again?
Okay.
Good. That's our projection formula, right? Okay, V2 dotted with W1 will be 0, 0, 2, right? So 2 over W1 dotted with itself is also a 2, isn't it? Yep. So I just get 101 back again. We agree? So it was kind of a easier one because notice that your V1 and your V2 are already orthogonal. But just to go through the process then, your W2 will be what? It's your V2. They're not orthogonal to each other, I lied. Your V2, oops, let me write it in terms of the formula first. V2 minus the projection of V2 onto W1. So it'll be your V2 minus your W1, well, the projection, which is the same thing as W1. And what do we get? We get negative 1, 1, 1. When I subtract. Now you can check this vector is your W2. It should be orthogonal to the first one, right? When you take the inner product of those two vectors, you should get 0. You should be able to check at every step what's going on. Okay? Yes.
So, instead, two, let's see, this.
You should be able to check any pairwise or pairwise at every step and see that the dot product is 0, inner product is 0. All right. So the next thing we want to do is compute the projection of V3 onto your. We're going to use W as your subspace. Remember again that at any step, at step I, your W is the span of the previously computed W's. Okay. At any given step, it's always the span of the previous ones. Okay. So with your V3 here, you'll do your W1 dotted with V3 over W1 dotted with itself times W1, and then you do the same thing, except replace the ones with 2's. Every step is a projection. You just have to project it on the previously formed vectors and add them together. Every single step is a projection vector. Okay? That's actually the really nice part about this particular process is it's easily programmable for one. Okay? All right. So let's do, here's my W1. Here's my V3. W1 dotted with V3 is 2 plus 0 plus 0. I get a 2 again, right? And we already did that was a 2 before. Now I need to do W2 dotted with V3. Here's my W2, the one I have the arrow next to, right? Here's my V3. I get negative 2 plus 1 plus 0, so we'll get a negative 1 over 3. Oops, I used the wrong one. Negative 1, 1, 1. The negative 1 is your dot product, your inner product with the W2 and your V3, right? Negative 2 plus 1 plus 0. this 3 is negative 1 squared plus 1 squared plus 1 squared. Yeah? So what do we get? Well, this 2 over 2 will just cancel itself out. So I get 1 plus a third, we get 4 thirds. 0 minus a third, so I get negative a third. And then 1 minus a third gives me 2 thirds. That's not your new W3, right? What do we have to do to figure out W3? So, yeah, subtracted the V3, right? Your V3 was 210. Your projection is 4 thirds, negative, good grief, negative 1 third, 2 thirds, which gives you what? 2 thirds, 4 thirds, negative 2 thirds. Are we now out of vectors? Yeah, we're now out of vectors, right? So we're done. So what's your orthogonal basis then? What are your vectors in your basis now? 1, 0, 1. Good. Good. There's the orthogonal one. Legitimate, right? Yeah. It's just doing the same thing over and over again. It's just your projections will get longer at each step because you're going to get more vectors, right? So if I had another vector, if I had one more vector, I would have 3 terms in the sum when I do my projection, right? Because I'll have 3 vectors that I created previously. So at each step, you'll get one more term in your sum as you go along. But yeah, it's literally the same. It's the same thing over and over and over again. So that's an an orthogonal basis. What would you need to do to compute it, convert it to an orthonormal basis? Orthonormal again means what's the magnitude of each of the vectors in the basis? 1. So what would I need to do to convert this to an orthonormal basis? Yeah, divide each one by their magnitudes. Yeah, make them all into a unit vector, right? So if you want an orthonormal basis, you do 1 over the square root of 2 times 1, 0, 1. 1 over the square root of 3 times negative 1, 1, 1. And then 1 over the square root of something not fun. 4 ninths, 16 ninths, gives you 25 ninths, 29 ninths. I did my arithmetic right? No, I did not do my arithmetic right. Try that again. 4 and 16 is 20 plus 4 is 24 ninths. Sorry. I did not do my arithmetic right the first time. And again, what are we doing there? We're just doing 1 over the magnitude, right? We're just creating unit vectors. That last step is easy, right? The last step is literally just make a unit vector out of each one. Okay. The hard part is getting the orthogonal basis. All right. Let's do another example. You'll notice that on your printout, I noticed it after I already printed it. On your printout, you'll notice that there's some vectors missing, so you might want to write them down. All right. So this one's an orthonormal, it says create an orthonormal basis for the subspace spanned by these 4 vectors. The first thing we should do is make sure that you actually have linearly independent vectors here. They won't span all of R5 because there's not enough vectors, right? That's why it says find a basis for the subspace they do span. But going through the process here, supposing that they are linearly independent, If they're not, you'll come up with a 0 vector along the way and you would just throw it out. All right, so what's your first vector going to be?
1, negative.
Okay, 1, 1, negative 1, 1, 0, 0. Pardon me. Then your W2. Oops, let's not do your W2. We need to do your projection first, right? Your projection of your second vector onto the first vector. So you'll do your V2, which is this one, right? I'll just write it down. Your W1.V2 over W1.W1 times W1, right? Okay. When you do the dot product of those two vectors, what do you get? Negative 1 over 3. And then it's times that first vector. Now we'll do the subtraction. You'll do negative 1, 0, 0, 0, 1, and then minus negative 1/3 times 1, negative 1, 1, 0, 0. What do you get? Negative 2/3 minus a minus a minus, so you get negative 1/3. Whoop, yeah, that's right. Minus 1/3, and then what do we get? Minus, it's a 1/3 times 1 will give me a positive 1/3, and then 0 and 1 when we're done. That's the W2. Good. Yep, that's right. As you can tell, there's a lot of computations, right? There are several ways that you can do inner products, but let me show you one way to do it with matrices. If you know how to do lists on your calculators, you can also do inner products that way. If you want to know how to do that, I can show you. I was going to show you how to do it with matrices because we've already talked about how to multiply matrices, right? So you can do this on your calculator, but I want to do it on GeoGebra, not GeoGebra, wrong one, Desmos. You can do it in GeoGebra too. Okay. So let's say I want to do an inner product. Well, remembering that if you do an M by N matrix times an N by M matrix, what size do you get? M by M, right? So if I do a 1 by, say, a 5 in this case, and a 5 by 1, I can multiply and get a 1 by 1, and that'll give you the dot product, right? In general, if you do a vector, if you think of them as columns, and you do a vector transpose with a vector, you get the inner product of that vector with itself. Okay. And generally speaking, I can do a W with it. It doesn't matter that it's the same vector or not. So, what was our first vector again? Oops, let me do it this way. Okay, so I want to make it a, we got 1 by 5 in the first one here. Oh, let's make it a, that doesn't matter. What was it again? It was 1.
No, 1. But 1, negative 1.
Let me do a, let me do a 5 by 1 this way. 5 by 1. Okay. What was it again?
1.
1, negative 1, 1, 0. Enter, and I'm going to put the other one in there too. So the other vector was negative 1, 0, 0, 0, 1. Okay. All right. So if you wanted to do the dot product of A with its, do A transpose A, not E, A. and you get 3, right? So it tells you what the answer is there. If I wanted to do the inner product with A and B, I would do A transpose B, and that gives me -1. This is what we had before, isn't it? Okay. So you can do these on your calculator using the transposes. Again, if you are familiar with lists on your calculator, you can do them that way too, and I can show you how to do that later. You can do a sum of a product of a list, and a product of 2 lists, and I'll do that as well. It just gives you a little bit more of a easier computational way to do it rather than have to do it by hand all the time. Okay. Right? All right. So just to do one more step, I'm not going to go through all the steps because I want to do the next example too. What would the next step be without going through all the computations? Okay, good. Yep, your projection of V3 onto W, right? So you would do your W1 dotted with V3, W1 dotted with itself, minus W1, oops, W2 dotted with V3, W2 dotted with itself. Is that your next vector? No, what do you have to do to find your next vector? Good, you guys subtract them, good. V3 minus the projection, good. Find that one, and then do the following one. I'll write up a solution so you can see the rest of them, so you can see the steps, but I want to do the next one as well. Is the process making sense a little bit? I know we haven't done too many examples, but it's very, very repetitive, right? It's also tedious, but it's very, very repetitive, isn't it? Okay. All right, so let's do the next one just to give you another example with a different inner product. So we've already talked about this before. We want to find an inner product, we define our inner product on continuous function spaces with integration. In this case, we're just going to focus on the interval from -1 to 1, and we'll do the inner product from as being the integral from -1 to 1 of the product of the 2 functions. And I just want to convert this into an orthonormal basis, okay? Well, what's your first vector going to be? 1, because that's what it says to do, right? That's what the process does. The first vector is the first vector, right? Now I want the projection of W2 onto W1. That's how we do it, right? But now what's our inner product? Our inner product is integration, right? So what are we going to integrate on the top? E to the x dx, right? Because it's 1 times e to the x. What are we going to integrate on bottom? Yeah, it'd be 1 squared, right? Because it's 1 times itself, right? What are we going to multiply it by? 1, because that is the W1, right? Yeah. Okay. On bottom, you get 2, right? The constant function you're integrating over an interval of length 2. So just take the constant times the 2. Okay. On top, antiderivative for e to the x is e to the x. You'll plug in 1, you'll plug in -1, so we'll get e minus e to the -1. And then it's times a 1. So that is the projection. Doesn't look pretty, but that is the projection, right? So what is your W2 then? Ooh, hey. What is W2 going to be? Yeah, e to the x minus that projection. Okay. That's it. That was it. That was the whole but we're done. That is all we have to do, right? We ran out of vectors, okay? So an orthogonal basis then is what? So your first vector in your basis was 1. Your second vector in your basis is that thing, isn't it? But that's not orthonormal, it's orthogonal, right? What do you need to do with each of those to convert it into an orthonormal basis? Divided by their magnitude, right? Now, we've already done one of them, well, a piece of one of them. What is the magnitude of 1 in this space? Wait, careful. 2 is related, but it's not quite 2. Square root of 2, right? Because that's magnitude squared, right? Remember that it was the dot product with itself, so that's the magnitude squared, right? So your first one will be 1 over root 2 times a 1. The other one, I actually have to do the integral, right? I'm not going to do the integral. I'll leave that for you. The square root of, I mean, it's not hard. It's just ugly. Square root of -1 to 1 of e to the x minus e minus e minus e to the -1 over 2 squared dx, right? I'm not doing that in my head. It's not bad. You just have to do it. The integral of the product of the functions, right? So if I'm doing magnitude, I have to do the inner product with itself. That's where the squarings come from. I have to integrate and then take the square root. That is what the magnitude is. It's just nasty. Yeah, nasty looking. It's not that bad. It really isn't that bad, did it, right? You just have to square it out first. All right. That's what a computer is for. Computer will give you that integral. Calculator will approximate that integral. All right. Is the process okay though? What we did? That one was ugly function. I agree, but not that bad, right? Okay. So the idea behind this is that we're going to use this idea of projections and this, especially orthogonal projection, to come up with the idea of least squares. Again, if you've seen statistics, you've probably talked about least squares lines for data. We're going to extend that idea to finding least squares solutions for approximating functions. Okay. So a couple of things that we'll do is that you've probably done least squares lines, but maybe you haven't done least squares quadratics or least squares cubics through points. We'll do some of that. But we'll also do, here's a function. I want to try to approximate with a certain set of functions and see what I get. Okay? So that's what we're going to do next time. All right? So we'll do least squares stuff. Including, we'll do some what we refer to as Fourier series stuff, which is to approximate functions with trig polynomials. Okay? And that sounds like fun. Okay. Yes?
When's the next exam?
May 6th, I think.
Oh,
Well, May 2nd. Maybe it's May 2nd. My probability exam is May 6th. It's one of the two. Yeah. It's sometime in May. All right. All right. Any questions at all? All right. Have a good one. We'll see you on Monday.